So today is our last day in hydro. So I'm going to go over homework 6, which, did anybody look at it? All right. So a couple of you looked at it. So we'll go over it. Some of them I might put on the final. Some of them I certainly won't. So some of the longer derivations I won't put on there just because if you haven't done it already once, then it's not fair to ask you to do it on a test. But some of them are like, here's a conservation law. You guys know how to deal with conservation laws. So some of them, and I'll go through what I think is fair and reasonable. So I'm going to go through homework 6, which kind of culminates our magnetohydrodynamics section, and then I'll go through everything that I think that I've talked about and give you guys. I'm going to flip through the homeworks and say we did this problem and we did this problem, and I'm probably not going to ask you that problem, but I'm probably going to ask you that problem. So I'm going to flip through the homework since I'll draw mostly from that, since I know that's what you guys put your hands on. Yeah, so let's get started. So, did anybody here play Majora's Mask? Y'all should, it's really good. They released it again for the Switch, which I think was a good move. I'm playing through Ocarina of Time, and it's still really fun, even though it feels like super old. Like, video games really didn't help, don't hold up well. Yeah.
Majora's Mask gave me nightmares as a kid.
That's understandable. Okay, so the first question that I asked, given the magnetic diffusivity and length scale L, write an expression for the decay time scale of the magnetic field. So he kind of does this in the book, but this is really a look at the equation and wave your hands at it real hard. So d by dt of B equals del cross B cross B plus lambda del squared B. So we didn't go through it with the induction equation, but we went through it with the Navier-Stokes equation, and we talked about it with the induction equation. I didn't make you do it, but this term is what's responsible for the actual decay of the magnetic field. This one can make it smaller a little bit by pushing on it in just the right way, but really this term does amplification and mixing around and smearing. This one does the decay. So if we just think about this in units, I've got something that looks like B over time on the left-hand side. So the derivative is just a fraction, right? If you're a physicist. Equals, we'll ignore this term, equals lambda B over length squared. So B's on both sides, so that'll cancel out. So it doesn't matter how big the field is, only how big it is. So let's rearrange this. So the time scale for all of this magnetic energy to decay is L squared over lambda. So it doesn't matter what the value of the magnetic field is so much as how large it is. Because that's really, I've got some big old volume with magnetic fields in it. I got to get magnetic field out of that by mixing it around with other stuff and decaying it. And that's just going to take me this much time. So this is a very simple expression. It's just the length squared over the magnetic diffusivity. And magnetic diffusivity is just the bit that shows up in the induction equation. Does that make sense? It's pretty straightforward. So then the next question is, what is the largest, for a 10,000 Kelvin plasma, what's the largest structure with a decay time shorter than the age of the universe? So we just use this equation and we say, well, in the book, he says that for a 10,000 Kelvin plasma, lambda is 10 to the 7. This you can just look up in the book. It's right there in the text. There's a more complicated expression for lambda involving temperature, but he did it for 10,000 Kelvin gas, and so I did too. Why 10,000 kelvins? Did I ramble about why 10,000 Kelvin? So if you have ionized hydrogen, so most of the galaxy is ionized hydrogen. Most of the universe, in fact, is ionized hydrogen. Most of the baryons in the universe are ionized hydrogen. Ionized hydrogen can cool by several different lines. So it's got all of these different ways that it can cool. So if you have a proton and an electron, they can scatter off each other and not get attracted, but just scatter. And that scattering radiates energy. Because anytime you move a charge, it radiates a photon. So when I have gas that's at about 10,000 Kelvin, it can cool by radiative processes in the ionized gas. But once it starts to become neutral, once it's less than 10,000 Kelvin, then you don't have all of those cooling lines from the ionized hydrogen. And atomic hydrogen doesn't cool as efficiently. So the universe likes to be at 10,000 Kelvin. At 10,000 Kelvin. There's a lot of bits of the galaxy that like to hang out at 10,000 Kelvin. There's a lot of bits of the galaxy that hang out at 10 Kelvin too, and I don't really understand. I don't have as good an answer why. So okay, we have this magnetic diffusivity. So we just say we just solve this for L. So L equals lambda times time. What's the time? What's the age of the universe?
Old.
What's that?
Old.
Old.
14 times 10 to the 9 years.
Yeah. So T is like 14 times 10 to the 9 years. And this is in centimeters squared per second, right? So, and we need a square root of that. 10 to the 9 years times pi times 10 to the 7 seconds per year. And lambda is 10 to the 7, and you get a square root of this, and I get a length scale that is 10 to the 12 centimeters. That's a number that's so large that I have really no intuition for it. How big is that in terms of the solar system? Does anybody know off the top of their head? It's right up there. So that's like a tenth of an AU. An AU is the distance from the Earth to the Sun. So just with this really simple hand-waving arguments, an object that's like the size of the solar system will take the longer, a magnetic object will take, just by diffusivity, longer than the age of the universe to decay. So things decay very slowly in outer space. Magnetic fields decay very slowly in outer space, largely because the time scales are so large. So in the interstellar medium. In the sun, the length scales are smaller, so those will decay a lot faster. You have a lot more magnetic decay in the sun because it's smaller. It's also higher density, and it also has a lot higher diffusivity because of the higher density and higher temperature. The sun is higher temperature than that. So the sun has things that decay, but in the interstellar medium, you have these structures that'll stick around for a very long time. So in a lot of astrophysics, you can throw out the diffusion term and just leave this term, because that's all that's going to work. Yeah.
Can you explain again, what did the temperature, like how did that affect the...
Yeah, well, I glossed over that part. It's not really in here. So the temperature sets the lambda by kind of a circuitous way. It's kind of complicated. So basically, to find lambda, you write down an equation for the electrons and you write down an equation for the ions, and both of these have a collision term in them. And all of these things depend on density, and you can get the resistivity by working through these collision equations, and the temperature comes out of that. I don't have a better answer than that. But it's somewhere in the derivation of this. So this goes with this, but I wouldn't ever ask you to calculate a diffusivity because we didn't ever talk about that. So I'll hand you that if you need it. Okay, the next problem was hydrostatics. So I said derive some stuff in the book, which I'm not going to go over in class because I did it already in lecture. So that's recorded somewhere. So this is basically just go through the magnetohydrostatic stuff. Watching me do it again isn't particularly useful. Let's see. Yeah, we'll skip that. Actually, I like this bit. Given Alfvén's theorem, describe why radial pinching is unstable. So this this setup is a magnetic column. Where you've got some column of plasma that's got a magnetic field around it. And we talked about how radially pinching is unstable. And the easiest way to see that is if I take a little parcel of field and I squish it. So let's say I take all of this field from the center inwards out to here, and I squish it radially, then this volume gets smaller. So then we move to something like this. So what happens to the magnetic field lines inside? If the volume gets smaller, the magnetic field energy, or the magnetic field strength goes up because of Alfvén's theorem. So as I squish the column, the magnetic field goes up. And there's a term that looks like minus b phi squared. And this term is in opposition to the pressure. So as you radially contract the gas, the magnetic field goes up, the tension term goes up, and it starts to pull in even harder. Does that make sense? Okay, Alfvén waves. Given a magnetic field strength of 4 microgauss, a density of atomic hydrogen of 100 particles per cubic centimeter, and a temperature of 10 to the 4 Kelvin, what is the Alfvén speed in centimeters per second? Not an unpleasant thing to calculate. This is the kind of thing that might show up on the test because it's really pretty straightforward. So the Alfvén speed, VA, is B over 4 pi rho, square root of that. This is equal to, what did I say? 4 times 10 to the minus 6. 4 microgauss is 10 to the minus 6 gauss. And then we're left with 4 pi. Oh, there's a square root missing in my solution. 4 pi divided by times 100 particles per cubic centimeter, but you got to multiply by the mass because we need the mass density, not just the number density, times 100 times the mass of the proton, square root of all of that. Now, you're left with something funny because here now I'm left with what are my units? I'm left with a Gauss divided by the square root of a gram cubic per cubic centimeter. Those are the units. And I'm going to tell you that works out to be a centimeter per second. Do I have a good, I don't know if I have a good, a better derivation. I realized that I got to this point and I should have had a good derivation of that off the top of my head as to why a Gauss is like that. I don't have a good answer. I have a good answer, just not off the top of my head. So anyhow, the Gauss is kind of a funny unit because it's not by itself. The Gauss is a CGS unit, and it is made out of centimeters and seconds and grams. Unlike the Tesla, which is its own free unit. You need mu knots and epsilon knots to convert between Teslas and kilometers per second. But the Gauss, if you keep everything in CGS, then a Gauss over a square root of a density gives you a velocity. Another way to see that is in just the constituent equations. F equals QV cross B. Maybe that's not a good way to see it. That's a good way to get it, but it's not a useful way to see it. A more useful way to see it, than the way I always do it, B squared over 8 pi is the magnetic energy density. being the magnetic energy density, it is in ergs per cubic centimeter. So a Gauss squared, and this is going to be in Gauss squared. So a Gauss squared is an erg per cubic centimeter. And this is every time I need to go think about the fundamental relationships between Gauss and centimeters, I always go back to this equation because it's simplest. The energy density is b squared over 8 pi. 8 pi doesn't have any units. I'm just leaving it there for consistency. Being an energy density, that's in ergs per cubic centimeter. And you can work out that a Gauss is, what's an erg? An erg is a gram centimeter squared per second squared per centimeter cubed. So let's erase some centimeters. So we just get a centimeter on the bottom. And we get a square root of that. And that's equal to a Gauss. So a Gauss is equal to the square root of a gram. Maybe that centimeter can't come out. I don't know. There's a square root. Whatever. It's kind of ugly, however you want to write it. A couple of different ways you can write that down. But regardless. Velocities from magnetic field strengths. That's the important takeaway. The important takeaway is that the Alfvén velocity, and that's the velocity that a magnetic field, or that a propagation travels down a magnetic field, a transverse propagation, is equal to b over square root of 4 pi. All right. And I got 2 times 10 to the 6 centimeters per second, which is a kind of a big number, but isn't really that fast. Well, 1,000,000 centimeters a second. That's 10 kilometers a second. Is that right? Can I count? Yeah, it's 10 kilometers a second. Which is kind of quick if you're in outer space, but not particularly fast. What is the sound speed in this gas? So how do you get the sound speed? C sound equals C sound squared equals gamma p over rho. Equals P equals rho RT. So this equals gamma RT. And so I didn't really tell you what gamma was. So gamma is probably 5/3. Although I usually use gamma equals 1 for reasons of outer space cools really effectively. So then C sound equals the square root of that. So I wrote it here as the square root of kBt over m, but that's the same as r. And you get 1 times 10 to the 6 centimeters if you use gamma's 5/3, or 9 times 10 to the 5 if you use gamma equals 1. And that's slower than the Alfvén speed. So magnetic propagations travel faster than sound propagations in this cloud, which is not unreasonable for molecular clouds. What is plasma beta? Plasma beta, and this is a thing I do expect you to remember, is P gas over P magnetic. And it describes how strong the magnetic field is in the plasma. It's what the plasma cares about for the magnetic field. That's easy to compute. We've got rho RT divided by B squared over 8 pi. So the magnetic pressure is D squared over 8 pi. The gas pressure is just rho RT. And you get 216 for the gas that I described. So what does that number tell you? That tells you that the gas pressure is substantially larger than the magnetic pressure. Probably large enough that you can ignore it, but not always. But the Alfvén speed is really high. So then the last question is, if 2 clouds of atomic hydrogen collide at 15 kilometers a second, which is a typical cloud collision velocity, so clouds probably collide with each other in outer space. So what's going to be the dominant physics? If I have 2 clouds of these magnetized clouds and they smash into each other, what physics is going to be dominant? Is it going to be Alfvén waves, or is it going to be shock waves, or is it going to be sound waves? So you just compare these three velocities, and I get a value of 1.5 times 10 to the 6 centimeters per second for the flow speed, but the Alfvén speed is 10 to the 6. So these are about the same, but it's much larger than the sound speed by almost an order of magnitude. Oh, it's exactly the same if you use 5/3. Huh. I need to write that problem a little better so it's a little more obvious. So anyway, shocks are going to dominate in this cloud because our flow speed is equal to the sound speed. Okay. So here's a problem that I actually debated eliminating. Given a sphere of gas, show that the ratio of its magnetic energy to its gravitational binding energy is conserved. So do any of you guys know the gravitational binding energy off the top of your head, the formula for that, for a sphere? By the sphere of radius r and mass m. The gravitational energy is some number. We're going to call it A. For a hard sphere, you get 3/5. M squared over r. Now, the binding energy is always going to go something like m squared over r because of units. And the magnetic energy equals, did I write a fake value there? Yeah. Some other number, b, times b squared. This is the magnetic energy density, so we need to get the whole magnetic energy, r cubed. Now, okay, it's a sphere, so it should be 4/3 pi r cubed, but I don't care about the 4/3. We'll just stick that in b. So now the ratio of GE to BE, what is this? So this is how much gravitational energy there is to how much magnetic energy there is. So if I have a magnetic field threading this blob of gas, then if the magnetic field is strong enough, if the magnetic energy is larger than the gravitational energy, then the magnetic field can support the cloud against collapse. So that's kind of cool. One of the things that's hard about astronomy is star formation is a really slow process, and we don't really understand why. So if you look at clouds of gas, so you guys all did the free fall time, right? If we look at a cloud of gas and say, what is the free fall time of this cloud of gas? It's an order of magnitude shorter than the actual lifetime of the gas, or 2. So we can see, for instance, the Orion Nebula, which is in the Orion constellation. The Orion Nebular cloud is 10 million years old, but it has a free fall time of 3 million years. And only 4% of the gas is in stars. So why is this cloud still held up? Why does the cloud exist at all anymore? It should have turned into stars 7 million years ago. One postulate that isn't right, but has been talked about for 40 years, is that magnetic fields hold up these clouds of gas. The magnetic field is actually irritatingly chaotic, so it actually can't hold up a cloud. But we didn't know that until recently. And some people still cling to this field, this idea. So let's just ask, what would happen if the magnetic field, so ignore the fact that it doesn't really work, this is an idea that people have been using for a long time. If I have a magnetic field that's supporting my cloud, how does that evolve? So let's look at this ratio. This is m squared over r over b squared r, let's take that r downstairs, r to the 4th. So now what does this do with time? B squared r to the 4th, that's b squared times the area squared. B times area, this is Alfvén's theorem. B times the area is conserved. Just like omega times the area is conserved for the vorticity of a fluid. So the magnetic field times the area is conserved, so the magnetic field times the area squared is also conserved. So this is a conserved quantity over a conserved quantity. So the ratio of gravitational energy to magnetic energy doesn't change. If I've got a sphere and it's magnetized and I squish it, the magnetic energy goes up, the gravitational energy goes up, both in concert. So you need some way to get rid of magnetic fields if this is how stars are going to form. Does that make sense? So magnetic energy goes like m squared, gravitational energy goes like b squared r cubed, and that combination goes like mass over flux, which are both conserved. Let's see. So you got to do something weird if you're gonna have something collapse with magnetic fields in it, if that magnetic field is strong. And from there we can talk for hours and hours and hours about the role of magnetic fields in star formation, which I will not bore you with. I think this is the last one, right? This is oh no, actually the last. So the last problem is derive the dispersion relation for the MHD equation, which I'm not going to make you do on the test. It takes a minute. So the second to last problem, this one really might show up. That's a hint, like not a subtle one. Because I like this problem, and it ties together a bunch of things that are that show up a lot. So the sun is a problem because where do stars come from? And I think I understand the actual answer about why the sun is a problem, but I think I just figured out on Monday. Most of science doesn't really know why, doesn't really understand how stars form. So this is part of the problem. So I've got this big ass cloud of hydrogen gas. It's H2. And we can see that stars all form in clouds of H2 gas. Actually, we can't see the H2. It's invisible because it's too cold. So we see other things. But anyway, regardless, there's big clouds of molecular gas. These big clouds live in the galaxy, which is differentially rotating. So this little cloud lives here, and it is rotating with a period of about the period of the galaxy. So it's got a period T of like 250 million years. This cloud is rotating. What happens when it collapses and gets really small? What happens to its spin rate? It goes up, right? Because from Kelvin's theorem, vorticity times area is conserved, or I omega is conserved, which are not the same thing, but basically the same thing. So this omega is not the bulk rotation of the gas. Omega is the vorticity in the gas. It's a microphysics thing. But angular momentum of the gas is conserved, so I omega is conserved. The interstellar magnetic field is like a microgauss. So there's like 10 to the minus 6 Gauss, which is 10 to the minus 10 Tesla, which is little if you work in Tallahassee, but very large if you're the vacuum of space. So we have a microgauss, and what's going to happen to that microgauss field as this thing collapses? There we have Alfvén's theorem, and that says that B times A is conserved. That says conserved. B times A is conserved. So when A goes down, B goes up, right? Let's put some math on this and see if it works out. So the cloud of gas is rotating with a rotation period of about 250 million years. Sorry, Squirrel Brain is providing all kinds of interesting factoids that you guys don't need, so I gotta work through all the other things that I'm not saying. So this thing is rotating with a period of about 250 million years. It has a size let's call our size L1 of a couple of light years. What did I call it originally? Oh, I said that it has an interstellar density of 100 particles per cubic centimeter, and we're going to form the sun. So, how big is the original cloud? So the original density is 100 particles per cubic centimeter. The original mass density is mass of the proton times 100 centimeters. So that means I need, so mass is conserved, right? So the size of the cloud cubed times the density is going to give me 1 solar mass. And I'm wiping out factors of 4/3 pi r cubed, or 4/3 pi. So the size of the cloud, r, is just equal to the original mass of the sun divided by the mass density of the cloud that you're started with to the 1/3. So this is the original size of the cloud. And that's, what do I get? I got 10 to the 18 centimeters, which is a few light years, which is, I wrote it here as 2 times 10 to the 7 r sun. I wrote it as r relative to r sun because that's going to make the math easier in about 9 seconds. So I omega is conserved. That's the same as saying mr squared over period t is conserved. So t is just 1 over omega. And the moment of inertia is just mr squared. Okay, there's factors of like 3/5 in here that I'm sweeping under the rug because I don't care about them because they don't matter. They all just cancel out. So the rotational, the angular momentum, let's call it J, is mr squared over the period. And that's conserved, so m1 r1 squared over t1 equals m2 r2 squared over t2. So we know r1 is a solar radius, we know r2 is 10 to the 7 solar radiuses, radii. The masses cancel out, and so you get the rotation period of 19 seconds. Now you've watched videos of the sun. It does not spin around every 19 seconds, right? It takes like 25 days. That's the end of the problem. That's a problem. Where does all this rotational angular momentum go? And it really goes into fragments. This whole thing, its rotation does not contribute. And there's a process called violent relaxation that we talked about in XGAL that as of Monday, I think that's really the core of how stars form. But they made this plot, and I'm like, oh shit, it's violent relaxation. That's what's going on. So this is what's going on. So the rotation of the sun is way slower than you would think that it should be if you just take the initial material and you collapse it. The initial magnetic field is the same. We get the same story if we do the same kind of stunt with the magnetic field. So with the magnetic field, Br squared is conserved. That's the magnetic flux. So B1 R1 squared over equals B2 R2 squared. And from that, the initial field is about a microgauss. If you just collapse it straight down, you get, what did I say here? 10 to the 8 Gauss. That is a whopping 14 orders of magnitude too large. So the upshot is stars don't come from big ass clouds of gas that slowly, once and for all, collapse into a thing. They come from big ass clouds of gas that get crazy violent and beat the shit out of themselves and then form stars. So this simple process of a nice big molecular cloud turning into one star is not where they come from. However, our understanding of chaos and turbulence has only really developed over the last bunch of years. So it's not surprising that these things go. So we got to get rid of angular momentum, and we've got to get rid of magnetic fields, and I think I know how to do that now, but I'm not 100% sure. So that's the homework set. Does anybody have any questions on that one?
You did post it, right?
I did post it and the solutions. All the solutions are up, and I realized that the solutions for homework 4 were forked. So there's a homework 4 fixed in the files that has the solutions to everything. I was writing one of the solutions right before I posted it, so I wrote that solution and only posted that one. I had turned the other problems off in the slide deck or in the parameter file. Okay. Now what do we? Yeah.
I have a quick logistical question about number 4. So for number 4, we use a bunch of equations for like the alphane velocity and then like the speed of sound.
Yeah.
And whatnot. I know you said that beta is something we should know always, but for the equations for A and B, would we be given that, or would we have to like derive it?
You should know the alphane speed. You should know beta, and you should know the sound speed.
Okay.
Just write those down. There's not a ton of things that I. Here, actually, let's make a running tally of things that I think you ought to look up first. We'll do it on this board. And I debated, so I make XGAL open book just because there's so many little factoids, and I want to have the facility to ask you any of those little factoids. Since this class is really a lot more about process, I don't. But yeah. Okay, so the alphane speed is b over 4 pi rho. That's not the first thing you should know. First thing, actually, can I get this? This isn't the board that doesn't come all the way over here, isn't it? Yeah, it goes there and stops. We'll just turn the camera. Burp. Okay, so. Man. So Navier-Stokes, you should know that. And how to get it. Euler is just Navier-Stokes without the diffusion term. Comes from the same place. Continuity is the density equation. You should know how to get that one too. I'm not going to write these guys up. If you want, I can. I was flipping through the exam for the last time I did this, and man, it was hard. But I put those equations on the beginning of the exam. I don't think I'm going to this time because I don't think the test is going to be quite as hard because I'm not going to ask you to derive alphane waves. Also, the first question was derive the gene's length, which I think might be a little hard, but maybe not. Maybe that's a good one. I think you guys could do that. So, basically, know these guys. You should know these guys pretty cool by now. You should also know the MHD equation, which is just Navier-Stokes with the Lorentz force. And you should know the induction equation, which is this del cross B one here. Oh, not that one. It's somewhere on this board. I think it's on this board, right? If you want me to go through any of those, and that's is true for the rest of everything that I'm rambling about, feel free to stop me and make me talk about it because I'm just kind of running through everything. Then we also said alphane speed, sound speed, which is CS squared equals, remember the derivation, the definition, dt d rho. It's partial p partial rho. And then if you have an adiabatic gas, P rho to the gamma is a constant. No, I'm sorry. P over rho to the gamma is a constant. Squirrel brain. P equals rho to the gamma. Also remember what adiabatic means, but okay. I will fill that out as we go on. Actually, should I start with my notes or should I pull up? I'm going to just pull up the homeworks and just put them up. Because that way you can be like, oh yeah, I didn't understand that one. So this will go kind of quick. Stop me if you want me to slow down. Okay, so the first homework set was just some math stunts. So why is the curl of the gravitational force 0? Do this thing in tensor notation. I think everybody's solid on tensor notation now. What does the curl of V tell you about the field? Div V, what does it tell you about the field? Do this thing in cylindrical coordinates. Close the book and derive Euler and continuity. That's a running thing. That's it. And then how long did this take you? I watch you leave, so you don't need to answer that one. So from the first homework set, there's not a ton that's going to explicitly show up. It's mostly going to be stuff that you've already worked on. So that homework set doesn't have a ton to offer you, except for that last one. Let's see. Find an expression for the convective derivative. That's pretty straightforward. That kind of thing might show up. We talked about Bernoulli's equation. So here we had this bottle problem where we use Bernoulli's equation. So that's just this lovely dude here. Totally fair game. Because I think it's a nice kind of system to work with. You get intuition from it. Derive the internal energy equation. That's hairy. I probably won't ask you to do that because that's just long and it's easy to get stuck in the weeds. Plane parallel Couette flow. Totally might show up. So remember, this is shear when you have two moving surfaces and they're moving past each other. No slip boundary on the boundary condition on the ends tells you what the boundary conditions are, and then integrating the eta del or the new del squared v term gets you what v is doing in between the plates. If you want, I can go over that one a little slower. Oh, and I'll have office hours before, so the final is Thursday. I got to do office hours on Monday because Tuesday and Wednesday are both hairy for me. Does that work for everybody? But it's what you got. You guys got a horrible Tuesday, don't you?
We have a Monday
We
final.
have a GR exam on Monday morning, so
Okay,
We're gonna be
probably
burnt out.
won't start studying for this class until after that.
that's understandable. So I'll do them at 4:00 on Monday, just because that's well, that jives with that. But my afternoons, Tuesday and Thursday, I have other exams that I got to proctor. Okay. Reynolds number. Estimate some Reynolds numbers. I think those problems are really funny. So, and I like seeing what people come up with. So I may have you write down some Reynolds numbers or estimate some Reynolds numbers, just because it's an interesting exercise. RE equals LV over nu. You should know Reynolds number. I didn't pull up anything else that Navier Stokes. Oh yeah, Bernoulli. We should know Bernoulli. And Bernoulli's easy to derive. It's just conservation of energy. But it's easier to remember it. Yeah, so we went through a bunch of those. And that was it for that homework set. Let's see, homework 3, derive the momentum equation. I'm not going to put that out there, but I might make you do it. Just because it's not super painful or long. But knowing how to get the momentum equation from the Navier-Stokes is a useful stuff. Dispersion relations. So remember that V phase is omega over k, and V group is d omega dk. So remember those bits. Remember how to get a dispersion relation. So that was just dispersion, and then we showed that the sound speed, which is defined as dp d rho, can be written as gamma k over mass times temperature. It's not a painful thing to show. Might show up. Not a thing that I'm probably going to put on the final though. But it's a thing you ought to be able to do. The Rankine-Hugoniot jump conditions. Don't memorize them. But they may show up. So these are the jump conditions across a shock. And you remember how to get those. I have an interface, and I have conserved quantities that look like dq dt plus div f equals 0. If we just integrate, we set the time derivative to 0 when we integrate across the step function, so you just get a step function in f and the flux. So the real stunt in deriving the Rankine-Hugoniot equations is just writing things in a conservative form and then integrating. We did a little bit on Berger's equation. I'm probably not going to put it on the final. But I do like it. So we use Berger's equation to show that this thing blows up. So part of a boiler is really ready to explode. And we did method of characteristics for this, which I'm also probably not going to put on the test. And then we derived sound waves. I'm going to write method of characteristics there, put it in parentheses just on the off chance I'm probably not going to do anything there. Oh yeah, sound waves. Linearizing things and perturbing things. So those are themes that showed up quite a lot. Use some Fourier analysis. Let's see, homework. So that was the first half of the class. And then we had some turbulence. So we talked about diffusion. Should be familiar with diffusion. The board gets really hard to write on when it gets down this low. Yeah, so we did some with diffusion, mostly just as a useful thing. Derive an expression for the convective derivative of vorticity and vortex tube stretching. So these are the major equations. I don't think I'll leave a little space in case there's some more. Vortex tube stretching. So it's be good to remember that. How vortex tube stretching worked. How to get the Reynolds stress. That's another thing. Yeah.
This isn't the fixed homework set, right?
No, this is homework 5. Homework 4 was the fixed one.
I thought
Oh,
this was homework 4.
no, we're on 5 now. Oh, I moved on to homework 5. Yeah. Oh, did I skip 4? Oh, I just went over 4. I'm sorry. Ah, yeah, thank you. Sorry. Derp. So jeans length. You should remember how to get the jeans length, which comes into all of this stuff. And as I said, so we went through the jeans length really cheap, where we did it just based on dimensional analysis and said it should kind of look like this, and then we did it with the full derivation. Both of those I think are good potential final things, because I like both of them. We did interface instabilities. So with the interface instabilities, I won't ask you to go through that derivation again because it's really long, but I might present to you, and I won't ask you to memorize that dispersion relation either. So if I have any questions on that, I will provide the dispersion relation for you. Or if I add any problems about that, they'll be pretty nerfed so that you can actually get them done in 2 hours. Because those instability things kind of take forever. But it's worth remembering. It's also worth remembering all the instabilities that came out of that. So we had Rayleigh-Taylor and Calvin Helmholtz, and we didn't talk about Rickmeyer-Meshkov, but it comes out of there too. And we talked about gravity waves. So those instabilities were all pretty fun and show up in all kinds of places. I think I'll put the camera on this. I'm not really holding still. But I wouldn't ask you anything as hard as problem 7, which was take that 2 interface instability business and add surface tension. That's a little long. And then I asked you some questions about the jeans mass just using the values, so you should know what the jeans mass is. But I'm not going to ask you to just write it down cold because that's a just boring kind of problem. We talk about some jeans masses. And 5.5, so 5.5 is take Navier-Stokes and find the energy dissipation rate, which I like as a problem. So make sure that you there's not a solution in this homework set. Maybe that'll show up, maybe not. Odds are low because I didn't put the solution in the homework set. Okay, that finishes the first semester, or the first half of the semester. Then we're on to homework 5. Vortex tube stretching, Reynolds stress, turbulent cascade. So the cascade and diffusion. So make sure that you can derive the cascade. That's a hint. So make sure you understand that that cascade, and think about the length scales in the problem while you're doing that. Who does what where, and when and why. So you can do it qualitatively, where we just talk about it, and quantitatively, where you actually solve the equation. Oh, good. And then we also talked about Richardson diffusion. So this is a Richardson diffusion problem. So there's two kinds of diffusion. There's inertial range diffusion, which is Richardson diffusion, and there x squared goes like t cubed. Then you have turbulent diffusion, where you're larger than the, where their structure is larger than the inertial length scale of the turbulence, and that develops like x squared goes like t, like a diffusion process. So one is super diffusive, and the other one is merely diffusive. Okay. And then that's it. That's up for homework 6. So let's see. So we got this list of stuff that came out of the homeworks. Let's see. I also made a list. Oh, and then MHD stuff. So what do I expect you to know from MHD? So I ran out of space. Let's put a little here. So I understand what an Alfvén wave is, how fast it goes. You should understand Alfvén's theorem. And that's that magnetic flux is conserved. Goes right by the dA.
No.
You should know about the decay time. You should know how the equations work. We talked a little bit about dynamos. I'm probably I might ask you about the anti-dynamo theorem. Probably won't make you derive it because that's kind of a hand-wavy derivation anyway. Yeah, let's see. So I made this list, probably going to show up. So here's things to know. If you're comfortable with all of these things, it's kind of a lot, but we've been working on them all semester. If you're comfortable with all of these things, you'll be fine with the test. Like that here. So problems that I like, that are really, really likely to show up, that you should definitely study. So okay, derive Navier-Stokes. That's a question I like to ask. Or continuity. Or if I'm feeling generous, maybe only Euler, because it's a little easier. Linearize things. And Fourier analysis. And stability. Know when something's going to blow up. So we get things that look like e to the I kx. And if k is imaginary, or omega is imaginary, then things explode. You should be familiar with what the Reynolds number does. And why we use it, and what we use it for, and what it tells us, and what we can do with it. Turbulence. And I think that is just the same thing I wrote over there. The cascade is important. Richardson diffusion. Is important, and then turbulence diffusion. then Alfvén waves, Alfvén theorem. Those are useful things. Anything else? Anything else that you guys want to talk about or ask about of all the stuff that we've done? We've got about 5 or 10 or 15 minutes left. That is everything that I think of when I think about this course. Let's pull this guy over here. So some subset of this will be on the test. Well, I'm going to try to make it so that you guys can get it done in about 2 hours. Yeah.
Could you write down the MHD and induction equation?
Yeah. Yeah. Where should I do it? I'm not going to erase that because I just spent all that time. I'll show both of these. Can I show both? So the MHD equation is d by dt of v equals minus 1 over rho del p. That's just the pressure term. Oops. Derp. Fucked up right away. Let's start over. dv dt plus v dot grad v, that's the derivative of velocity, is minus 1 over rho grad p. This is the pushing. Plus 1 over 4 pi rho del cross b cross b. This is the Lorentz force. Plus nu del squared v. So it's just like the induction equation. It's just you got to remember this part. And this part we can also write as grad 1 over 8 pi b squared plus 1 over rho outside plus 1 over 4 pi rho b dot grad b. That's this term too. So I would recommend that you think about both of these ways to write this down. If I'm feeling generous, I'll give you the vector identity that gets you from here to here. That's not one that I expect anybody to know off the top of their heads. But it's just one vector identity that does this. So let's just look up at the back of the book and drop out the vector identity, and this guy falls out. But we have two different interpretations of what these two things are. So this is J cross B, where J is the current that's flowing in the plasma, cross with the magnetic field. In this formulation, we think about this as pressure and tension. And I really professionally think about it this way far more often because it's much more intuitive and it's easier to do math with. This triple cross product is kind of hairy to do any math with. All the identities that I know involve making it into this one first. So that's the MHD equation. Now I harried it up though. Let me make it prettier. There we go. And the induction equation is del cross B, which again has this triple cross product. And again, I like to expand this out and make it those 4 terms. This one turns into 4 terms, one of which goes away. The other one sometimes goes away, but 2 of them don't. Plus lambda, the magnetic diffusivity, del squared B. Anything else I want to say about that? I think no, not right now. Anything other questions that they want to talk about, or things on that board that you're like, I don't remember that. Can you just talk about that for a minute? I can do that too. Otherwise, I might punt early. Yeah, if you guys are all good, then we can call it for the day. And I'm gonna try to remember to erase the board before I get in. Or maybe I won't. Kind of depending. Office hours Monday. If I forget, just show up. Test on Thursday at 12:30 here. I can't think of anything else. Talk to you guys soon. Have a good weekend and good luck with the rest of your finals too.
Thank you.